So incidentally, I think I changed the homework deadline, but I forget whether I did or not officially on the website. So it is postponed by approximately a week for the fourth homework. Let me just check if the notification shows. Assignment. What happened? It's not even showing this. Oh.
Yeah, so it's showing in my site like 22nd May.
Okay, good. Okay. So before that, this weekend I'll put up another problem set. But okay, we can postpone. I mean, ultimately we'll have to catch up with all of them. But let's see. So did anybody hear anything from the Senate about? I mean, SEC about?
So I asked UG Dean and he responded with one word: patience.
Okay.
So yeah, that's probably all we can do right now. I'll ask again. I'll let you know if there's any response at all.
Yeah. Yeah. So is he generally responsive? How do you find this, Dean?
Notwithstanding personal remarks, administration in general has not really been very responsive when it comes to students making queries.
Yeah. No, that is what happened. So that's why they take all this. So we are very good at taking feedback, but not doing anything with them. So I mean, this is I mean not about him in general.
Yeah, precisely.
Yeah. Well, let's see if they. But as I said, course-wise, I don't want to completely shortchange those who want to learn things. So what I will do is I plan to do all the classes, whichever officially, unless they give a week off, I'll do all the classes and cover some reasonable amount of material. But in the for exam and other things, I will give it off. Okay, so that is, I mean, I'll give off. We'll discuss that at the end. If it is too heavy, I can leave out a couple of topics for the exam. So, okay. Okay, so now let me start. Let me start recording. Oh, it's already started recording. Okay, so it's already recording. Yeah. So okay. So what did we do last time? It was about Lebesgue spaces, right? About Lebesgue spaces, and actually I got Lebesgue spaces, but there was only one space I introduced, namely the space called L1. L1 is the, well, first of all, we have to move from, this is a general notion you have to get used to in measure theory. And after a while, which is that if two measurable functions differ on a set of zero measure, we think that they are basically the same function. Of course, they are not exactly the same function, but we introduce an equivalence relation whereby they become equivalent. Instead of saying they're equal, we'll say they're equivalent. That's just to satisfy our conscience. We don't call them equal, but only equivalent. But so it is it's something that you get used to. At least, for example, for me, it has become so ingrained over years that it is I never think of the function value at a point. I mean, it's kind of I have to force myself. So usually when I see a function, I mean, I only think of it as being fuzzily defined. It's not defined at any particular point, but it is defined almost everywhere like that. So anyway, so you don't have to reach that stage of insanity, but you can look at this L1 space, which is the collection of equivalence classes of integrable functions. Okay, and of integrable functions. Okay, and then it becomes a normed vector space where you can define this norm as the integral of absolute f, where f is any representative of an equivalence class. And we showed this very important theorem of Lebesgue that this is complete in this norm. So this is the theorem I have been alluding to from earlier, which kind of gives a justification why Lebesgue integration is doing a good job. Okay. Now I want to go on. Any questions about this, though? So I gave a proof. Basically, you have to take a Cauchy sequence and get a limit. So the idea was to take the Cauchy sequence, and first we get a limit which converges almost everywhere. Meaning we get a subsequence which converges almost everywhere. And then, so that gives us a candidate function for the limit. Convergence almost everywhere is not same as converging in this metric, but nevertheless, that gives a natural candidate. one thing that is I mean, I may not get much time to spend on these modes of convergence. It can't converge to one function. You can't have a sequence converging to something almost surely, and to something else in this metric. That can't happen. What can happen is it may converge in almost sure sense, but not in this metric or vice versa. That can happen. But it can't converge to do different limits. So if you get an almost sure limit along a subsequence, that gives you a natural candidate for the limit in this sense also. And we showed that indeed that actually, so first we got this, and then we indeed showed that f minus fnk it's also goes to 0. So the subsequence converges in L1. And since it was Cauchy, the whole sequence will converge in L1. That was the proof. Okay. So this is not a complicated proof. It's a nice proof. The key point was monotone convergence theorem, which is not there for Riemann integral. That is where we got this f from. Where did we get f from? Okay, we got f from this fact from this here. Okay, so you will see that. So the monotone convergence theorem, which is not there for Riemann integral, is what makes the difference. Okay. Okay. So now I want to, yeah, are there any questions, by the way? Any so far? So if not, let me proceed. So I said Lebesgue spaces, but I only introduced one of them. So now let me introduce the general Lebesgue spaces. Okay, more general Lebesgue spaces. So these are LP spaces. So maybe I change color to make it clear. Yeah, let's continue with LP spaces. L is for Lebesgue, LP spaces. So for p greater than equal to 1, define. Okay, so we are working in this setting of xf mu, and f is any measurable function. Okay, so we define the p norm of a function. First we define it for function, just like with the LP norm. Later we will move to equivalence classes. So this is defined as integral over x mod f to the power p. We raise absolute value to the power p d mu, and then whole to the power 1 over p. See, this is always well defined because mod f is a non-negative function. So the integral is well defined. It could be infinity. That's where we are going to cut down. We will concentrate on those for which this is finite. And that will give essentially the LP space after I move to equivalence classes. So this is called the LP norm. It's only a pseudo norm. So why is it only a pseudo norm? So let us look at this. So again, norm alpha f p is, if you put alpha times f, here you will get alpha f raised to the power p, right? So that mod alpha to the power p will come out of the integral, but then there is another 1 over p, so that will come out as mod alpha finally. So this is clear that this is okay. So okay, I have not yet restricted to things which are finite, but this is anyway true. This is correct. It is also, what else is needed? Is this true? F plus g triangle inequality would require this. Why is this true? Okay, so this is homogeneity. So I'm checking the norm properties just like with L1. In L1 case, it was easy. So for L1, we did discuss these points. If I take norm F1 was integral mod F, then alpha F norm is mod alpha times this, and the triangle inequality was obvious because this was integral of mod F plus G. And I just used triangle inequality to say that is less than equal to mod F plus mod G, and then separate the integrals by linearity. So I see that the L1 norm of F plus G is less than equal to L1 norm of F plus L1 norm of G. Okay, so that is fine. But actually that's not so obvious in here. So this one is not obvious in fact. So this is not obvious. So we will prove. We shall prove it, but for now accept that that is true. In fact, this is the reason why we restrict to p bigger than equal to 1. If p is equal to infinity, so this is why we don't allow 0 less than p less than 1. You could also have taken p between 0 and 1. Homogeneity part is okay, and it will be a non-negative quantity, but it fails this triangle inequality. That is why we restrict to p greater than equal to 1. So I will discuss that. Okay, so we have to discuss this. But let's keep that aside, accept it for the moment. But still, it won't be a norm because of exactly the same reason that this norm of p equal to 0 if and only if this integral is 0. Norm of p, the 1 over p is irrelevant, so this has to be 0. That means mod f to the p has to be 0 almost everywhere, which is the same as f equal to 0 almost everywhere with respect to mu. Okay, so this is why it is a pseudonorm. The second point we will discuss. Okay, so for now take it for granted because I don't want to interrupt the discussion. That takes a little bit of an argument to prove that. But so accepting that, so this gives a pseudonorm. So we move to equivalence classes. So we move anyway. I have not restricted to things which are finite at the moment. Yeah, so now this is greater than equal to 0 is always okay. But as of now, it can even be infinity. That doesn't make sense. We have to restrict to things which are finite, but still this fails. So we restrict. So LP of x f mu is defined to be all equivalence classes of f such that the p norm is finite. This is well defined again and again the same thing. If f and g are equivalent functions, that is they are equal almost everywhere with respect to mu, then their norms p norms will be the same because you see you can replace one by the other, the integrals won't change. So this is well defined, so it doesn't matter which representative I am taking. So this is a so claim is this is a vector space with a norm. So we claim, so the theorem or fact will say, what is it? Yeah, claim. Let's write this claim. LP of xf mu is a vector space with norm. So what will we define as the norm of a equivalence class here, meaning an element of LP is just a norm, LP norm of any element of that. Okay, so this is well defined. Whenever I write this, you have to always be cautious that it is well defined because I took a representative, but it shouldn't matter which representative I take, and it doesn't. So that's why. Further, so claim that is 1. 2 is that the most important thing, LP is complete under this norm. It's complete under this norm. So the first part is actually, so the proof is not difficult. Everything is analogous almost except the triangle inequality, which I have not proved. But modulo that, we can give the proof. Well, that first part is a vector space is okay because alpha f, if you take alpha f plus beta g, what is its norm supposed to be? By definition, it is actually, so the alpha times equivalence class of f plus beta times equivalence class of g is the same as the equivalence class of alpha f plus beta g. But that is same as, by definition, that is the what I defined as the LP norm of the function. So we are being a bit loose in notation. The same norm P is used for equivalence classes as well as for functions. but that is okay because functions in the same equivalence class will have the same norm. Okay, so that's okay. But this, so this is by this one. So this is called, this is not obvious, we shall prove. It is called Minkowski's inequality. Yeah, that's called Minkowski's inequality. So this is by Minkowski's. We can write it as less than equal to alpha f non p plus beta g non p. And now by homogeneity and so on, this is just alpha times norm fp plus beta times norm gp, which is finite. Hence, this is a vector space. That means if f and g, okay, if f and g are elements of this, so this is if f and g are elements of LP, then this is finite. Therefore, this alpha f plus beta g is also having finite norm. Therefore, hence it's an LP of mu is a vector space. In our case, we are always taking reals. Many a time it is actually sensible to take over complex actually. All analysis, it makes sense to do it over complex numbers. But since in this part there is no big difference and we have done it over reals, but you can do it over complex also. That's not a problem. But since I have, but you can also change. I mean, you can do everything over reals, and at the end you can see that when it's complex, you can modify in a simple way. So let me do everything over R. Okay, so vector space over R. But when you're reading books, just be cautious which one they mean. Sometimes they define all functions to be complex valued rather than real valued. Okay. But you see, the problem is when you define integration and so on, you have to go through simple functions. That is okay. Complex valued simple functions would be fine. But positive doesn't make sense in complex. So there is a supremum you have to take. Anyway, you have to go through real valued functions. And the integral of a complex valued function would be defined by summing the real and imaginary parts, etc. So let's stick to R. Okay. So this is a vector space, and that it is a norm is also okay. So norm fp is greater than equal to 0, and equality if and only if p is 0, which is same as f equal to 0 almost everywhere with respect to mu, which is same as saying that the equivalence class of f is 0 in LP. So that's why this is a norm. So that completes the proof of 1. What about the proof of 2? It's actually very similar to L1. Just one difference is there. If you try to copy it straight, you will get into a trouble. Okay, so still we are working under assumption that we have proved in Minkowski, which I will come to. If you try this, you will get into one trouble. Maybe it is better. I will. Should I transfer it to a problem or should I just indicate how this is done? Okay. So maybe I'll just indicate. So very similar to L1 proof. Let us just go over the L1 proof. Okay. So what happens? Again, we will take a Cauchy sequence in LP. Okay. So by definition, you will find N1, N2 dot 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 such that this happens, right? For that. So let's write that step. Okay. So let me just write a few steps. I won't write everything. So suppose F1, F2 is a Cauchy sequence. In LP of mu. Then find as before N1 less than N2 less than N3 and so on, such that Fn minus Fm P norm is less than 2 to the minus k if M and N are greater than equal to capital Nk. This we can do by Cauchy. In particular, fnk plus 1 minus fnk is less than 2 to the minus k. That's all for all k. Okay, fnk plus 1 minus fnk will be smaller than equal to 2 to the minus k. That is okay. But then what did we do? Here we just summed the integrals of fnk minus fnk plus 1 and concluded that this sum is finite. Here there are all these pth powers which may look confusing. Okay, if you try to follow it at this point, here instead of pth power 1, we have p. That means the sum of what is the sum that is finite? It is the sum of this type of integral with the power p raised to the power 1 over p. Actually, that both the powers p can be annoying. So, but it's the way we do it is not like that. So let's say we have this. What this means is that we use Markov inequality. Okay, so we don't directly, we want to say, so what is it we want to conclude? So this is just a small point which would be good to keep in your toolkit, how to argue when you have this kind of stuff. Okay, so that's why I'm going over this step. So we want to prove again that summation mod fnk plus 1 minus fnk converges almost surely. If I show that sum is absolute, sum is finite almost surely, that means that the series converges almost surely without the absolute value, right? So this is what we want to prove. But how will I get it from here? Because all these are pth powers. I mean the pth norms. So they don't look like this. So we have to argue it. And the point is we use Markov inequality. And you look at the set where fnk plus 1 minus fnk is bigger than, let us say, so let's make it here 2 to the minus 2. Okay, then since I have written the k, let's make it minus 2 to the minus k by 2. Okay, suppose I look at the set where the difference fnk plus 1 minus fnk is bigger than this tiny number 2 to the minus k over 2. That by Markov inequality, I claim this is smaller than how much? What can I compare it to? I want to compare it to the integral over x of fnk plus 1 minus fnk raised to the power p d mu. What is the prefactor here? See, so let me write here. Markov inequality is, as I stated, is that if g mu of mod g bigger than equal to t is less than 1 over t times integral mod g d mu. Okay, this is Markov's inequality. The point, and this is where the great power of Markov inequality comes, you need not apply it to your function that is given. You can modify the function and apply. For example, I can apply it to g square. What will that give me? But I will say that this divided by, so let's take g square, t square, t square, and g square here. Okay. So that is also true, right? And now I call t square as s. So it is 1 over s times, sorry, what did I do? Sorry, well, I made a stupid mistake. So this is without any square, y square here. This is true for any t also, right? Now I call t as, instead of t, let me call it t squared, this is true for all t positive. So you can put t squared also here. So, but mod g square bigger than t square is same as mod g greater than equal to t. And but now I get a better bound, which is 1 over t square. So this is like Chebyshev inequality in probability. So like that, you can apply it to the power cube and so on. So the higher the moment you have, mod g to a higher power you have, the better bound you get for the tail of this, this measure. I mean, if g has to be integrable, if a larger power of g has to be integrable, then you would have its the measure of the set where it is large has to decay faster and faster. That's the whole idea. So instead of 1 by t, you get 1 by t squared, etc. So that's what we do here. So what do we get here? We raise this to the power p d mu is bigger than this power p bigger than 2 to the minus kp by 2. So what I get here is 2 to the kp by 2. Okay, I should correct the original. Let me assume here, I can put any sequence here. Let me assume that this is smaller than 2 to the minus kp. Okay, it's just now I realize that would not have been 2 to the minus k is not good if I take this. So let me take that to be 2 to the minus kp. Then the measure where it is bigger than 2 to the minus k over 2 is smaller than 2 to the kp over 2 times this. I hope this part is clear. It's just using this. G is this difference function, and g to the power p d mu is divided by t to the power p is bigger than the measure of the set where g is bigger than t. And t to the power p will give me 1 over t to the power p will give me this. Okay. And now what I have is the bound for this is that this is less than 2 to the minus kp. So I have 2 to the kp over 2. So I get a saving and I get 2 to the minus kp over 2, which is summable. Okay. So this is summable. Hence, this was the problem that was there in your midterm. And I also gave you a proof, another proof last time of this. If I have a collection of events whose measures is summable, then what we can say is that fnk plus 1 minus fnk is less than equal to 2 to the minus k by 2 for all but finitely many k. Okay, for all but finitely many k, and this holds for almost every x. Yeah, this holds for, so there is nothing. So the conclusion is if the sum of measures of sets is finite, then the set of points which belong to infinitely many of those sets has zero measure. So here to just to write here with x here. So if I write fnk plus 1 of x minus fnk of x, this is true for almost every x with respect to the measure mu. Okay, that's what it says. From here, you immediately get the conclusion. So for any such x, the sum of fnk plus 1 of x minus fnk of x is finite, right? Because this is smaller than 2 to the minus k over 2, and that is summable. Because, yeah, so that's all. And that gives me this conclusion that I was wanting. So that gives me this, that this sum is finite almost surely. The rest of the proof is almost the same. Because once I get the convergence of this series, what happened? So the main point was to conclude that that converges finite. I mean, that is finite almost everywhere. It's 4 o'clock. Once you do that, this series converges absolutely for almost every x. And so I just add up an fn1 to cancel the first term. And then this is just a telescoping way of writing the sequence fn1, fn2, fn3, and so on. From this, we get the conclusion that along the subsequence, we have a limit almost surely. And then you have to do something to say that that converges is in fact in LP. Okay, so that all that part is actually identical. So I will leave that out. Unless there are doubts about it, I'll leave that out. So I'll say that we have done it. It may be even a good exercise to go over it. Okay. Any questions here? So these LP spaces, I mean, why LP spaces though? I mean, so that may be one question one should worry. Well, who dreamed up these? Why are they important? I mean, they don't look particularly, I mean, is it necessarily something that you should consider? It's not that obvious actually. Why LP spaces? it's not actually obvious to me. I mean, you get used to it in time, but I don't know if a priori I can say that yes, these are things that you should consider. But I so basically what I question I got and I have no answer for you. It's like that. But what I will say is that special cases are useful to consider. Okay. Okay, there are three special cases that you need to worry about. In fact, you can think that the rest is somehow a filling in of those three cases. But slowly, as you see more facts, you get the feeling that somehow considering all the LP spaces is actually a good idea. But a priori, L1 is a very natural one. L1 is very natural. Okay, so another one is L2. So this is P equal to 1, P equal to 2, and there is one more which I have not yet introduced, which I will introduce, L infinity, when P is infinity. Everything I got was for P greater than equal to 1. Of course, I meant P less than infinity. But there is another space called L infinity. So these are three natural spaces. L1 we have done, so I don't need to elaborate on this. L1 is fine. So what is this L2 and L infinity? First, let me talk about L2. L2 is actually, we have just now defined, it's the special case. It is the set of all equivalence classes of functions such that integral f square d mu is finite. Okay, and with the norm of the equivalence class being just the integral of f square d mu square root. Okay, so that is what it is. So this is the L2 space. Now, what is special or what is nice about the L2 space? Okay, so let's bring L infinity later. Let me say a couple of things about L2. So L2 space is particularly special. We have already seen this is complete and all that, but there is something else special about it. What is it? Does anyone know? Compared to
It's
L1?
an inner product space.
Huh?
It's an inner product space.
It's an inner product space. So this is actually, we can write, this actually comes from inner product. Namely, we can define the inner product of two things as the integral of fg d mu over x. It is a fact that this is actually finite. This is the Cauchy-Schwarz inequality, which again we are going to prove in a moment. So if f, so the fact that if f square integral is finite and g square integral is finite, then integral fg is finite, requires a proof. Okay, fg is, so this is needs proof, but maybe you already have seen this type of proof many times, that integral f square finite and integral g square finite implies fg is integrable. Otherwise, I cannot define this inner product, right? So in fact, but so you can, so this will come. This is Cauchy. All the inequalities I am putting at the end. I will talk about inequalities in a few minutes. So that comes, and this is an inner product. So that is why this is actually, so this is L2 is a complete inner product space. Complete inner product space. So this is what is called a Hilbert space. It's a Hilbert space. So that is something, if you, when you take functional analysis course, you will be introduced this term. Hilbert space is, so the functional analysis is basically like linear algebra, except that it is you are studying vector spaces on infinite dimension with infinite dimensions. In your linear algebra class, you studied vector spaces over finite, over field, general fields, but of finite dimension, finite dimensional vector spaces. In functional analysis class, you study infinite dimensional vector spaces. But that already introduces a lot of complications. That's why your subject changes from algebra to analysis. You had linear algebra, it will become functional analysis. Why analysis? Firstly, there's very little to say about these infinite dimensional spaces unless you have extra structure. Just vector space structure is just too poor. So always the thing that you'll study in functional analysis will be infinite dimensional vector spaces over real or complex numbers, but with an extra structure such as a norm or a inner product. Norm, let us just for simplicity say norm. More generally, a topology is required on the vector space. Without that, there is very little to do about, very little to say. So that's what you will study. And prime examples are these things. So for example, just any infinite dimensional vector space over real or complex numbers with a topology is called a topological vector space. That is something you'll study, but really the things that you should care about are particularly nice ones are spaces like LP. Okay, these give the main examples of things that you will consider. So this is, for example, okay, or maybe this, let me write for all other P. So this is a complete inner product space. It is called a Hilbert space. For all P not equal to 2, LP is not an inner product space. So do you know how you can say that it is not an inner product space? It seems, if you have never seen, it's not an obvious thing, because to say it's an inner product space, you just have to produce an inner product, which what is anyway? Okay, I didn't complete it here. The point is, this comes from inner product means this is just means that what I mean is that the norm is square root of the inner product of an element with itself. So when I say norm comes from an inner product, it is always by this formula. Okay. So to say it doesn't come from an inner product seems complicated, because there are many possible inner products. How do you know nothing works? So you would have seen this perhaps. So do you know what? How do you say it's not an inner product space? Okay, I should say in general. Do you know how do you say a vector space? I give you a vector space with a norm, but you have to say it doesn't come from an inner product.
Oh, so maybe we can. I'm not entirely sure here. I'm just thinking aloud. Using the properties of the norm, try to disprove one of the inner product axioms.
But you are not given the inner product.
Right. Okay. I see. I see. I see. Oh, so I think we'd proven this in a previous course that any inner product will be. It's only a very restricted set of functions that you can use as candidate inner product. So we can probably prove something for that entire family.
No. Maybe you are thinking of something like in Rn. Every inner product is X transpose Ax, where A is a positive.
Right. Precisely.
That's what. Okay, but that is enough. That is very finite dimensional.
Ah, right. I mean, that can still be extended, right? A transpose, A being positive definite can simply be translated to a function or a binomial function.
Similar things. Yeah, that is a very good way of thinking, by the way. That's an excellent way of thinking. The way to think is, but here, actually, by the way, this has nothing to do with even, okay, let's actually, your point is right. But let me say that here we don't even, these are not even necessarily infinite dimensional. Okay, let me take back. The problem is not the infinite dimensionality. We can even take a 2-point space. So you take X is 1, 2, and mu is mu of 1 is 1, mu of 2 is 2. Okay, so now what is LP of this? So the power set, the sigma algebra is the power set. So I'm taking a trivial measure on a finite set. and I'm taking the simplest finite set. Okay, the second simplest finite set where you have 2 points. What is LP in this case? What are functions on this?
Functions on this, uh, right? So
f of 1 and f of 2, two numbers.
essentially, points lying in R2, right? Or C2 or whatever.
Yes, R2. All LP spaces are R2. Only the norm is different. That's all. Norm of, if I take a point in R2, I write as UV. The norm is different. In general, LP, the space itself changes, but in a finite setting, all functions are integrable and all that. There is no problem. So the space doesn't change, so to speak. The vector space is the same, but the norms are different. So the norm is mod u raised to the power p plus mod v raised to the power p. That is the integral of this function. uv is the function which takes value u at 1 and value v at 2. So we are writing such functions as a pair of numbers uv. Okay, that's what we think of. Then integral of mod f to the p is this whole to the power 1 by 2.
Is it that though? As in, shouldn't we have like a weight of 2 at the point 2?
Oh, sorry. This is I meant to put 1 at both points.
Right.
Yeah, right. If I put different weights, I will have weighted sum here. Let's not, I mean, since I'm giving examples, let me take the simplest example where the weights are equal. So when p, so this is for 1 less than equal to p less than infinity, and L infinity I have not yet defined, but as a motivation, let me give, this is a norm you may have seen, maximum of mod u mod v, that will be when p equals infinity. Don't worry about this case. So even in this situation, so actually this is, so by the way, this functional analysis doesn't have to be infinite dimensional. A lot of features are already there in finite dimensions. You can take this simplest, second simplest vector space, which is R2 with this type of, I say second simplest because if you take R, if you take a single point, you get LP will be R, but all the P norms will also be the same. Mod u to the power P to the 1 over P, they will all be the same. Okay, so that is too trivial. So this is already non-trivial. So you take this vector space with this. You take the first one. Okay, this is the no. Even here, the fact remains the P equal to 2, you get your usual u square plus v square square root, the Pythagorean distance, and this comes from inner product. Okay, so this is from uv. But other p don't come from an inner product. This is not have to do with finite. I mean, so how can you say that?
So in this particular setting, I think the matrix argument will work very well.
Okay, possibly. So you can try to do that, maybe. Yeah. So that is valid, but is there something else you can give?
Else. What's the direction in which we're trying to think here?
So you have given the norm, but you want to say this, it doesn't come from any inner product.
It doesn't come from any inner product. Okay, so we know given an inner product how to define a norm, that is known. So
Yes.
let's assume the norm comes from an inner product called whatever, rounded brackets or something, and then try to not entirely sure. Let me see.
Yeah, if you could write the formula for recovering the inner product from the norm, that would be one way. Yeah, let me tell you, probably, I mean, has nobody seen this? I'm a bit surprised. I thought in linear algebra class such a thing would be taught.
Parallelogram identity.
Yeah, so one fact that in any inner product space, so if V is an inner product space, yeah, so then norm of u plus v squared plus norm of u minus v squared is 2 times norm of u squared plus 2 times norm of v squared. It is parallelogram law or Apollonius law, something it is called, because if you think of this as u, this as v, I mean, Okay, not to be confused with this UV. This here U and V are vectors. So here is the origin and this is U plus V. What this is telling is that the sum of squares of the sides, the four sides, is equal to the sum of squares of the diagonals lengths. So U plus V is this diagonal, U minus V is this diagonal length. So this is the square of this diagonal, square of this diagonal. If you add that, you will get the sum of squares of all the sides. And this is actually an if and only if. Okay, this is an if and only if. So I won't go over it. You can think it is elementary point. Suppose this is satisfied, then you can write a formula for the inner product in terms of the norm. Okay, so that what you are thinking, Shekhar, is the right way. You should think how you write the inner product in terms of the norm. But it turns out that whether that is well defined. So the correctness for the well definedness of that will be exactly this. So this is the quantity one must check. And even in this simplest measure space, you can check this is not satisfied. Okay, so this is LP is not an inner product space in general, but it is a complete normed linear space. But it is a complete normed vector space. Linear space is same as vector space. So that is what is called a Banach space. So your functional analysis, as you go into functional analysis course, you can keep as your goal to understand Banach spaces. Hilbert spaces are a bit too special. That is, I mean, you have to understand Hilbert spaces, but they are a bit too special. They are very close to finite dimensional vector spaces. A lot of theory is very similar. But Banach spaces are different, and that is where that much of functional analysis you can say is about understanding Banach spaces. Because more general spaces, which you will be led to as you try to understand Banach spaces, but you can take that as they come. So, and the primary examples, one of the purposes of this measure theory course, as I had mentioned before, is to provide examples for your functional analysis class. So without this, so what other Banach space do you know? Complete non-linear space. Without doing measure theory, you would have very few examples to work with. One of the examples, for example, another example here is C01. If you take, or C of any compact metric space for that matter, C01 with Supno. So this is a complete non-linear space. The completeness is basically, I mean, something that you have seen. Uniformly Cauchy implies, I mean, there's a limit. Okay, so that's something you have done actually. It's just in a different language. So you would have very few examples, but with this LP, you have innumerable examples actually. It's not even just LP. I mean, there are many spaces called, when you study PDE, this was a motivation I gave in the first lecture, that when you try to study PDEs, you have to define the space of solutions in which you are looking for solution. And usually those spaces are called Sobolev spaces. They are based on LP. Okay, they are not exactly LP. Instead of LP, there will be a more complicated statement. LP is, roughly speaking, LP is set of functions whose pth power is integrable, right? Okay, it's equivalence classes and all that, but modulo that, loosely speaking, LP space is those functions whose pth power is integrable. Those Sobolev spaces will be things like functions whose second derivative, first and second derivatives are integrable, or their pth powers are integrable. Or maybe the first 7 derivatives, their pth powers are integrable. Such spaces. That is what you use in PDE. So this is, and you don't, all based on LP idea. Okay, so that's where this comes. So this, what we have done now will be very important. LP spaces are complete. They're complete non-linear space, and this. I haven't defined L infinity yet. So what I began saying is that LP gives you many examples, but I was saying there are 3 special cases which are nice. One is L1, very natural. L2 is particularly nice because it is the only Hilbert space among these. Now let me define L infinity, which I had not done. Okay, I mean, I put in a lot of other stuff between here in this discussion, but okay, now I go back to here. I was giving 3 special cases, 1, 2, and p equal to infinity. L infinity of x f mu. What should it be? In some sense, it should be the limit of LP spaces. Okay. What is the limit of the pth norm? Okay. So let's not worry about equivalence classes. Think of a function. Norm f p. What happens to this as p goes to infinity? That should be what L infinity is. Okay. So can anybody say what will happen to this as p goes to infinity? Oh, you can think of a more special case. Even here, you can think what happens to this quantity as p goes to infinity. What is the limit of, say, 2 to the power p plus 3 to the power p over 1 over p as p goes to infinity? What does this converge to? So it converges to 3. Is that clear? Because this is okay. This is greater than equal to 3 power p, and it is less than equal to, 3 power p over to the power 1 by p, which is 3. Right? If I drop the first term, I get it is greater than, but it is also smaller than 2 times 3 power p inside the brackets whole power 1 by p, which is 2 to the 1 by p times 3, which goes to 1, which goes to 3. So this is bounded between two numbers, which goes to always the maximum takes over. The thing is, when two distinct numbers, you have two numbers, they are raised to a very high power, then the higher number gets far more weight. Okay, so that's its weight, so relatively goes on increasing much more. So that's what happens in general when you take, you have a lot of numbers, the sum, well, integral mod f, this is like a sum, but mod fx is raised to power p. So the largest one of these will start taking precedence. But you have, it's a bit more subtle than that when you are in general measure space. So I define it. It is the set of all f, all equivalence classes of functions such that L infinity norm is finite. So it is the set of all equivalence classes of functions such that L infinity norm is finite. And then the norm you define here on this will be the L infinity norm, which I am yet to define. Will be the L infinity norm of any representative. So it should not depend on that. So that's where the subtlety comes. Suppose I were to define, so then going by what I said, the natural thing to define would be that L infinity norm of f would be sup over x mod f of x. Okay, what is the problem with this? This is not, this does not go well under the equivalence. If f and g are equivalent, their suprema are not the same. Right? So this cannot be transferred to the level of equivalence classes because you can just define, you think of a Lebesgue measure, real line and Lebesgue measure. At one point doesn't matter. So you can just define your function to take a very, very large value at one point. And that doesn't change the function in the sense of equivalence, but its L infinity norm defined like this goes up. So we should have a more robust definition which does not change when you change the function just on a zero measure set. So how do you define the thing? So it is sometimes called the essential supremum. So it is not, so what is supremum fx? It is the largest, it is a point beyond which no value is taken, right? So here we take the supremum of all values t greater than equal to 0 such that the set of values taken above that, or the inverse image of that, is actually zero measure. So you take the supremum of all t such that essentially that is the supremum. So this is called essential supremum. So that is what is the L infinity norm. Okay. Now this is, now it is clear that if f is equivalent to g,
Sir, you probably mean infimum.
oh sorry, yes, thank you. It's not supremum, but it is infimum. I want the smallest t. Yeah, thank you. So it is the smallest t such that above that the values taken, it's essentially it doesn't take the values above that, in the sense that the inverse image of mod f bigger than t, that has zero measure. Okay, so okay, so this is also a one. This is also a Banach space. So this is also a Banach space, not an inner product space. Okay. Well, okay. So this I have not proved. Okay, the proof I gave here doesn't apply here. So maybe the completeness is an exercise. Maybe this is actually easy. It is very similar to the completeness of C01 in the soup norm. Okay, if you have a Cauchy sequence, uniformly Cauchy sequence, what do you do? At each point, it is a Cauchy sequence. Fx, you have Fn, is a sequence of functions which is uniformly Cauchy. That means Fn minus Fm subnorm is going to 0. Then, if you evaluate at any point x, then Fn of x is a Cauchy sequence of real numbers. And so it has a limit. So you will define f of x to be that limit. For every x, you have the candidate. Now you have to show that f is continuous and Fn converges to f. So somewhat similar, a little more subtle is this. Exercise means you can also all read up. If you cannot do it yourself, read in a book. It's actually easier, much easier than the proof for general LP, okay? Or even L1 and LP, they are similar, but the L infinity is actually trivial. So I will just leave the completeness. Once you do that, you get the Banach space. So we have these prime examples of Banach spaces, namely LP spaces, along with the one special one, namely L2 space, which is the Hilbert space. Okay. Okay. So that ends this topic. So to except the inequalities, I have not yet proved Minkowski inequality or Cauchy-Schwarz inequality. We'll come to that in a moment. Any questions at this point? That's the next topic I'll do. Okay, so if there are no questions, so then I go on to the next topic, which is, let's write inequalities maybe. So there are a bunch of very useful inequalities, which I will just present here. So actually, I'll only present two, which I need. So let's do two inequalities. So we are in a measure space xf mu. So there are two inequalities I want to prove. One is called Holder's inequality. So what Holder's inequality says is that if f and g are non-negative measurable, then integral of fg d mu is less than equal to integral of f to the power p. Okay, for any 1 less than equal to p less than equal to infinity. So norm f to the p d mu times integral over x g to the q d mu. Okay, so this is raised to the power 1 over p. This is raised to the power 1 over q, where q is defined by this equation 1 by p plus 1 by q is 1. Okay, so 1 by p plus 1 by q is 1, and so for every f and g non-negative measurable, I take non-negative measurable because then I don't have to say integrable and all that, because anyway the integrals will make sense because they are could be infinity. This is also valid when this is infinity, in the sense that if the left side is infinite, the right side will also be infinite. All these things are well defined, right? No problem. So note that for every p between 1 and infinity, 1 by p is less than equal to 1. Okay, so what are these dual? So this is a relation which keeps coming again and again. 1 by p plus 1 by q equal to 1. In this entire LP space business, they keep coming. Well, it looks like a strange relation at first. Why sum of reciprocals? That may be simply because you wrongly labeled the LP spaces. Maybe they should have been called L1 over P spaces, in which case the sum of the indices would have been 1. So that's not a deep remark, but there is a deep connection between the LP space and LQ space where P and Q are related like this. Okay, so that is the point actually. So as we shall see, this is the first manifestation of the deep relationship between LP and LQ, where P and Q are like this. I will remark a bit more on this relationship, but as a corollary, so in particular, if F is in LP and G is in LQ, you see that I am already acting a bit loose in my language. F is not in LP, right? Okay, maybe I let me not use that loose language for now, since I am asking you to be a bit careful for a while. In particular, if F and G are now not necessarily non-negative with finite P norm and finite Q norm, then FG is in L1. Yeah, so then FG is in, norm FG in L1 is less than equal to the pth norm of F times gth norm of Q. Okay, so this is Holder's inequality. So let me just remark on this interesting relationship between P and Q. So what is this relationship between P and Q? For every P there is a Q like that. Okay, so before going to the proof, let me remark. So some pairs are, when P is 1, what is Q? When P is 1, 1 over P is already 1, so Q is infinity. Okay. When P is 2, 1 over P is half, so 1 over Q also should be half, so that they add up to 1, so Q is also 2. And when P is infinity, Q is 1. Of course, they reverse roles. So the line here is 1, here is 2, here is infinity. As I said, somehow the indexing may have been historically wrong. Maybe it should have been indexed by 1 over P, but don't bother, don't try to do that and on your own, because this is a very well established notation. Nobody wants to mess with this. But why I say that it may have been like that, because what is it? This, in some sense, 2 is the midpoint of this actually. That is why 2 gets mapped to 2 itself. 2 is to be thought in this LP spaces. 2 goes to itself. So here is, when P is 1, the Q is at infinity and vice versa. But 2 is mapped to itself. So as P goes up to 2 from 1, so if I take something like 3 by 2 here, it will be mapped to something here. Okay, I don't want to figure out what that is. So as you go up like this, you keep coming, P goes up from 1 to 2, Q keeps coming down from infinity to 2. That's how it is. And that is the relationship. And as I said, we'll see again and again, LP space and LQ space are intimately connected to each other in some strange way. Okay, so that is the fact. So that is one remark. Another remark is when P equal to 2, so then Q is also 2. What is this telling? This is just telling us the Cauchy-Schwarz inequality. This is telling us that Fg d mu is less than equal to integral f square d mu into integral g square d mu. This is called the Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. Okay, so that's a special case from here. So this is a special case of this. Okay, so it's a special case of Hölder's inequality. Okay, but also another easy. So this is something you can prove. You probably have proved Cauchy-Schwarz inequality in 5 different occasions, and the proof you can always base it on the same ideas. So it is easy to prove it. So, but the general Hölder inequality is not that easy to prove. Another special case that is easy to do is p equal to 1 and q equal to infinity. That case also you can see is not too difficult. So when p equal to 1, q equal to infinity, maybe I write down p equal to 1, q equal to infinity, what we are saying is integral fg d mu is less than equal to the L infinity norm of g times L1 norm of mu. Right, so p is 1 and g is q is infinity. So this is L1 norm of f times L infinity norm of g bits. So this is sort of clear, right? If you imagine the L infinity norm is like the supremum of g, then you can just bound mod g. This is mod f times mod g. Mod g you bound by its supremum norm and pull it out. Only it is mod g is less than equal to supremum norm almost everywhere, not everywhere, but that's okay. You can still pull it out under the of the integral. So this is also easy. This is actually easy. Okay, so this is easy to see. But the general case is not easy to see, and so the second one follows from first is obvious, right? You just apply the first one to mod f and mod g, that's all. You apply this to mod f and mod g, then you get this. So I have to prove the first one in the Hölder's inequality. Any questions about this? So this is a very important inequality, and let's give a proof. Have you seen it by any chance in some class? Anyone? I mean, in any of the, of course, not for Lebesgue integral, but any Hölder's inequality. Okay, so let me present. So the key idea in Hölder's inequality, I mean, so why this relationship between P and Q come like this? Okay, so let's first see that. So the key thing is an inequality just for positive numbers. Okay, so key observation. Is that if A and B are non-negative numbers, then A to the power P over P plus B to the power Q over Q is greater than equal to 1. Okay, so that's what this is. Oh, sorry, not greater than equal to 1, greater than equal to AB. Okay, again, always you think of the special case when P equals Q equals 2, then it's saying that A square by 2 plus B square by 2 greater than equal to AB, or A square plus B square greater than equal to 2AB, which is obvious because the difference is A minus B whole square, that you know. But you may or may not have seen this one. If I change the power on one side to from 2 to something, what should be the power on the other side? So it's not clear. So this is the inequality. Let's first take this inequality and prove it. From the observation, let's take that observation. Then so you take mod f, so at a point if you want, mod f of x to the power p plus us by p, but plus mod g of x to the power q over q is greater than equal to fx into gx. Okay, so this is true. I mean, actually, I was taking non-negative, right? I'm doing the first part. So let me remove all the absolute values and write it without that, just for simplicity. So integrate. You get, what do you get? So you get on the right side, okay, let's invert, reverse, fx gx or fg d mu. Since I got fx gx d mu of x over x is less than or equal to, 1 over p times integral fx to the power p d mu of x plus 1 over q times gx to the q times d mu of x. Okay, so this is this what we wanted? We get a bound for the L1, right? The integral of fg. Integral of fg d mu is less than equal to, except the right side turned out to be something else. I wanted some product f to the p d mu power 1 over p g to the q d mu over to the 1 over q. But what I got is something additive here, 1 over p integral f to the p. So this, without writing x, what I have written here is that integral fg d mu is less than equal to 1 over p integral f to the p d mu plus 1 over q integral g to the q d mu. That doesn't look like what we wanted, but actually it gives what you want. So this is one of the things to realize, that when in such inequalities, it is more than meets the eye, because this what we have put is not for a specific f and g, but for all f and g non-negative measurable, right? So you can change it. So how is this going to apply? So in general, so apply this. F divided by norm fp and g divided by norm gq. Okay, I can apply this. This is applicable to any two functions, so I can apply it to f by norm fp and g by norm gq. Okay, so if norm fp or norm gq is 0 or infinity, deal with it separately. See, those are trivial cases which you can deal separately. Okay, for example, if norm fp is infinity, what we are saying is the right hand side is infinity. So whatever be the left hand side, this inequality is true. So if one of them is infinity, no problem. This inequality is valid, right? But what if one of them is 0? Well, if one of them is 0, if norm fp is 0, that means f is 0 almost everywhere. So the right hand side is 0, but the left hand side will also be 0, because fg will be 0 almost everywhere. So I'm saying that if one of them is 0 or infinity, deal with it separately. Otherwise, we can do this. We can divide by it. Okay, now you apply it to this. So what does this give us to get? You will get f over norm fp g over norm gq over x d mu less than equal to 1 by p times integral f to the p by norm fp, norm fp to the power p d mu plus 1 by q integral, I am raising g over norm g to the power q. So I get g to the q over norm gq to the power q d mu. Okay. Now what is the right hand side? What is this integral? This integral f to the p is exactly this, right? F is non-negative measurable. So this is exactly 1 by p into 1 plus 1 by q into 1. These are 1 because norm fp to the power p is exactly f to the p d mu. We are working with non-negative measurable functions. So what is 1 by p plus 1 by q? That is 1. So what you have proved is integral of this is less than equal to 1, or integral fg d mu less than equal to norm fp into norm gq. So what was in additive form comes out in multiplicative form, and this is what we want. We want here norm fp and norm gq. So you got that, right? So is this okay? So I got it in a form. If I use this inequality for real numbers, I get something which doesn't quite look like this, but I apply it to f over norm f and g over norm g, or f over p norm of f and g over q norm of g, and then it works. Okay, so that is the complete proof. Well, except the inequality which I have not proved yet about real numbers. Any questions here? Is it okay? So only thing to know is, I mean, this is actually another fact about functional analysis. A lot of people think in analysis you're always working with limits, some infinite dimensional objects and so on. But actually at the heart of things, most things reduce to some finitary question actually. It may be an estimate about two numbers or finite set or something, and that's all there is often. Okay, so in particular, Holder's inequality hinges on this inequality for two real numbers. That's all. So let's prove this. Let's prove this observation. How do you see this? Well, there are different ways to do it. Let me give you a geometric way. So this, I have never seen it written in books for some, I don't know why not. This was how I was taught when I was an undergraduate student. One of our probability teachers showed this, and I have always liked this. It's where do you see a power p by p? You know, a and b are positive numbers. I mean, 0 is you can ignore. Anyway, there's nothing to do. So a and b are positive numbers. So where a power p by p, does it remind you of anything? Where does such a number come up naturally?
Integration.
Integration. So if you integrate, a power p by p is the integral of x power p. So if I take, let's say here is a, and let's assume x power p looks like this. Oops. So this is the graph of y equal to x power p. So then what is a power p by p is just the area under this curve, right? This blue area is actually a power p by p is the area. Okay. Now let us say b is here. I have taken b smaller than a, but it is the same. You can reverse the roles of them. So what is b power q by q? It is also the integral of some x power q minus, oh sorry, this is, I made a mistake. This is not correct, right? What is the graph here? What should I integrate with?
X to the power p minus 1.
This p minus 1, not p. It's when I integrate x power p minus 1 up from 0 to a, I get a power p by p. Now what is b power q by q? This is the point. So here is another view of the relation that we have said. If y is x power p minus 1, I say that it is the same is actually x is y power q minus 1. Why is that? See, our relation is 1 by p plus 1 by q equal to 1. Okay, just write it out. You get p plus q equal to pq, which is same as p minus 1 into q minus 1 is 1. Okay, so if you pull this to the other side, p minus q, if you expand this, you get pq minus p minus q plus 1, and that 1 cancels. So this is same as this. So p minus 1 and q minus 1 are inverses of each other. So when I look at y equal to x power p minus 1, it is same as x equal to y power q minus 1. So when I view it from this side, this is the graph of y to the power q minus 1. So what is the, so if I take this if I draw this line and mark this green area, this is actually area is B to the Q over Q, right? When you're looking at it, you now turn your head so that this is your x-axis and then this is the area. Now, clearly the union of these two covers the rectangle with AB. Okay, so this black area is actually rectangle has area and that is contained in the union of the blue and green region. So therefore it is the proof is by picture. Okay, so that's all. That's the proof. Actually, this is actually a deep thing. So this relation, many things can be said about this relation. There are other ways to derive it. Underlying the deepest point here is underlying all this is what is called convexity. Okay, convex functions are what underlines all this. I don't know if you people have ever seen convex functions, so I don't know if I want to go into that. Do you know what are convex functions? Well, if not, let me not get into this too much. But the relation, so x power p, so if p greater than equal to 1, x power p by p is a convex function. I mean, even if you don't divide by p, it is a convex function. This is a convex function. So it has a dual function called there is a what is called a convex dual. It's sometimes called Legendre dual, Legendre or Legendre transform. So this is something you would have seen if you have either taken some optimization course, convex optimization, etc., or if you have taken a physics course in mechanics. There is a quantity called Lagrangian and there is a quantity called Hamiltonian. The relationship between the Lagrangian and Hamiltonian is this thing called convex duality. So the relationship between x power p by p and y power q by q is that they are convex duals of each other. I have not told you what is convex dual because I don't want to go into that now. But for those who have an inkling of what is convexity or have either seen this in some other place, should figure out what I am saying. It will eliminate the situation. Okay. So, but maybe this is not necessary. We have given the proof. That's it. Okay, that was Holder's inequality. But what I wanted to prove, another one, namely Minkowski's inequality. What I want is Minkowski's inequality. So let's come to that. So let's take F G, non-negative measurable. Oh, no, not necessarily. Fg, so Fg measurable. Yeah, okay, no, I can, the easiest to write with non-negative measurable. And P is greater than equal to 1. You can also allow infinity here, but that part is not interesting. So let's just take P less than it. I mean, it's also true for infinity, but that's easy. So the statement is that f plus g to the power p d mu whole raised to the power 1 by p is less than equal to integral f to the p d mu whole raised to the power 1 by p plus integral g to the q d mu whole to the power 1 by q. Sorry, there is no q. There is all p. Sorry, I apologize. This is p. Everything is p here. So this is the statement, and in particular, if Fg are not necessarily non-negative, so they are measurable, and integral f to the p d mu is finite, and integral g to the p d mu is finite, then the LP norm of f plus g is less than equal to the LP norm of F plus the LP norm of G. Okay, this is exactly the way I had written earlier, because this will be the LP. Well, you will apply this with mod F and mod G. So you'll write this with mod F and mod G. Then it is clear, right? Mod F plus G will be less than equal to mod F plus mod G to the power P d mu integral to the 1 over P and then blah blah blah. Okay, the second will come from first. So let's not, I will leave that to you. But the key point is to prove the first one. So proof of the first part. How do we prove this? It looks, again, as I said, it's not trivial because it's not so obvious when you look at this. How will you get all this integral to the power P to the 1 over P is there? How will I extract F and G separately, right? When P is 1, it's okay. It's simple triangle inequality. But otherwise, it's not at all clear how you will extricate that. So again, there's a trick here, which I always forget. So how do you get it from Holder's inequality, for example? There are many ways to do it. One way is to do it from Holder's, or should I do it from here? I'm thinking, is it easier from here or is it easier from yeah, so P and Q. Right. Yeah. Okay. So maybe it can be done from here. But okay, let's do it from this. But I always forget what you have to apply. So let me just look up, because it is something I always forget. If somebody remembers, I can take that advice. But otherwise, I will have to. I want to write this. Right. So what do we apply? Yeah, okay. So here I'm just copying from Rudin's book, Real and Complex Analysis. So it is given that you apply this to, okay, F into F plus G to the P minus 1. I see. Okay. So Rudin says that you do, so you write, you consider F into F plus G to the power P minus 1. Okay. So now the integral of this d mu is less than equal to integral F to the P d mu to the 1 over P. We are using Holder's inequality, okay? And integral F plus G to the P minus 1, this function raised to the power Q d mu whole to the power 1 by Q, where okay, this part is, this is okay, right? So we are applying Holder's inequality to F and F plus G to the
It's
P minus
5 o'clock.
Okay, let me take 2 minutes to finish this. This will not take time. The key, I mean, it's certain. Sorry.
No, just a sec, sir. I was trying to wrap my head around what's happening here. Where did the Q come from in F plus G to the power of P
I'm
minus 1?
using Holder's inequality. So I take F and F plus G to the P minus 1. I apply Holder's inequality to that with P and Q.
Right, okay.
So which I do, right? I F and F plus G, I apply with P and Q. Okay, so the state the Q will disappear. You will see in a moment. So what is this? This is this is the, okay, this will write as norm Fp. What is F plus G to the P minus 1 into Q? P.
But to be able to do that, I think you need to show that F plus G whole power P minus 1 is in LQ.
Well, all this is non-negative, so we don't need to worry, right? Here, everything is non-negative, so the integrals are this way a form of writing. I don't need to worry about anything. It could be infinity, I don't care. It could be infinity also. You understand? So these are non-negative functions. So all these integrals could be infinite. I am okay with that. In Holder's inequality also that is allowed. All these integrals could be infinite in the first statement. In the second statement, when I write, these integrals are assumed to be finite. So okay, so maybe your objection, if your objection is to my writing norm FP, let's just leave it as it is. Let's write it as integral to the 1 over P. But what is this P minus 1 into Q? What is P minus 1 into Q? P minus 1 minus P minus 1 over P is 1 by Q. So P minus 1 into Q is actually P. So if I take 1 minus 1 over P, that is P minus 1 over P, that's equal to 1 by Q. So P minus 1 into Q is P. So this is actually again integral of F plus G to the power of P d mu whole to the power, however, 1 by Q. Okay. So this is what we get. And then you interchange the role of G and F. So you do G into F plus G to the power P minus 1 d mu. That is less than equal to what I get here is G to the power P d mu whole to the power of 1 by P. And then I get here integral of F plus G to the power P d mu whole to the power 1 by Q. Okay. So this same inequality, with G and F interchanged I do. So what I get here is G in place of F. That's all. Now you add this. What is it we get? On the left side we get F plus G into F plus G to the P minus 1. So that is F plus G to the power P d mu less than equal to, this part is common. So I have integral F plus G to the power P d mu but whole to the power of 1 by Q into integral of what is not common here is integral F to the P d mu power 1 by P plus integral G to the power P d mu power 1 by P. Now you see this, I take this to this side, 1 minus 1 by Q will make it 1 by P. To the power of 1 minus 1 by Q, which is 1 by P, is less than equal to integral F to the P d mu 1 by P plus integral G to the P d mu to the 1 by P. Done. It looks very tricky. I mean, it's I can never remember that trick. Actually, there are other ways to write which is less tricky perhaps, but this is very slick, like everything that Rudin does. So that's all. Any questions? Sorry, I went a bit over time, but that completes this Holder's inequality and Minkowski inequality. And next time I'll move on to another topic. So this essentially completes, okay, not entirely, LP spaces. The basic point about LP spaces are complete. There is a deeper relationship between LP and LQ which will come. I will mention it at least. Okay. So if there are any questions, you can ask.
Yes, sir. So have you looked at the end term date?
Oh, in term, so there was a date. I mean, so I know there is a schedule. I just looked at it. I mean, I didn't open to see when mine is supposed to be. But I thought anyway, after the discussion last class, I thought all these are probably subject to change. If there is going to be a week of break, then that will probably change. Otherwise, whatever date is given is fine with me. But if people who are crediting have a consensus and want to change it to another time, that's also fine. But you have to accept that and then do it. So,
right. So by the way, has the timetable been made available to students as well? Because I don't recall getting an email.
You did not get it, is it? Okay, so let me just see it right away. So revised, okay, there was a revised final examination. Okay, so I download it here. What is our class time? Tuesday. Is this the original class time or did we change? This is the original, right?
This is the original.
Tuesday, Thursday. Okay, why don't I just attach it and on Teams so that you have it? Where is it? Okay, so I will send it on Teams, but let me read out what I see right now. Oh, what happened to this? Where did it go? So ours is Tuesday, Thursday, 3:30 to. Where is that Tuesday, Thursday? Monday. No, what the hell? 3:30 to 5, right? This is all messed up. So what is it saying? Tuesday, Thursday, it is telling 3.
I mean, I don't think that's a very exhaustive list. Maybe we can just look for the closest time slot or something.
No. I do see something here. Tuesday, Thursday. Sorry, there is a Tuesday, Thursday, 3:30 to 5. It says Friday, July 11th afternoon. That's the very last.
I see.
That's the very last one. I will try to attach this to the Teams so you can have a look. I don't know to what extent this will change or not change, etc. But you can take a look anyway.
Okay, sir. Thank you.
But as I said, if there is a consensus among people to change it, I have absolutely no objection. But consensus is essential. Yeah, and just final examination. It's asking all sorts of questions. Okay, I have attached it on. I have sent it on chat to the Teams. Okay, to measure theory team.
Okay, so thank you.
Third.
Yes.
Yeah, in the first line of the proof, you applied the Holder's inequality, right?
Yes.
So for that, A plus G needs to be, LP.
No. What if it is not? So here I just wrote, see, f and g are non-negative measurable, then integral fg is less than equal to.
Okay.
But your point will come here actually. So there is actually, that is a point one should separate out, because when I divide out by this quantity here,
Yeah.
I should say that is finite, because if it is infinite, then there is no, if that is, okay, that place maybe one has to worry it is finite, but in the beginning, I don't need to worry. All are non-negative functions, so I just do it.
Okay.
Is that okay? Yeah. Any other questions? Okay, if not, okay, so if not, then I can close the meeting. I'll stop recording.